Late in the summer of 1977, an historic mission of exploration was launched. Twin spacecraft, christened Voyager 1 and 2, broke free from the Earth's gravity on journeys to the outer reaches of the solar system. Their primary destinations were the four giant outer planets: Jupiter, Saturn, Uranus, and Neptune. For 13 years, the Voyagers probed these mysterious worlds at close range, while collecting data and transmitting stunning images back to Earth. Among thousands of pictures of planets and moons, perhaps the most memorable was recorded on February the 14th, 1990, when Voyager 1 approached the edge of the solar system, then turned back toward the Sun. With its wide and narrow-angle cameras, the spacecraft captured unprecedented views of our home star and 6 of its orbiting planets. One of them appeared as a small pale dot, engulfed by a ray of sunlight. It was the Earth, from nearly 4 billion miles away. While the world gazed intently at this pinpoint of light, timeless questions about its meaning, purpose, and significance suddenly took on new relevance. And once again, as in ages past, we paused to consider our planet's role within the grand scheme of the universe. The mystery of the Earth's significance in the universe has challenged philosophy and science for more than 2,000 years. Early perceptions were shaped by the work of the Greek scholars Aristotle and Ptolemy. They taught that the Earth sat motionless in the center of the heavens while the moon, sun, and other stars and planets revolved around it. This geocentric view was the foundation of Western cosmology for 18 centuries. Then, in 1543, the Polish astronomer Nicholas Copernicus ignited a revolution. In his book on the revolutions of the heavenly spheres, Copernicus argued that the Earth was not stationary, but instead orbited with the other planets around the Sun. For the first time, a correct understanding of the mechanics and structure of the solar system was in sight.
The idea of the moving Earth seemed to violate some fundamental principle, but Copernicus somehow had the mental power to imagine what even to him seemed absurd. So he thought the impossible. The Earth moves. And once you imagine the Earth moving instead of the Sun, the mathematics of that cosmic machine started to make sense. It was the key that unlocked one of the great mysteries of the universe.
Copernicus had laid the cornerstone for modern astronomy. Yet, 400 years after his discovery, the empirical fact that our planet was not the center of the solar system had evolved into what is now known as the Copernican principle. The idea that the Earth occupies no preferred place in the universe.
Copernicus had a theoretical way of explaining the apparent motion of the planets across the sky. That's all it was. It wasn't a theory that told us whether or not Earth was special, or whether we played some importance in the scheme of things, or whether every place in the universe was the same as every other place. Nevertheless, this reinterpretation of Copernicus became prominent in the 20th century. It's often called the principle of mediocrity. This principle says that our location and our status are mediocre, they're unexceptional. As a result, we should not assume that we are in any way privileged or that the universe was designed with us or beings like us in mind.
The Copernican principle and the concept of the Earth's insignificance was popularized during the 1970s and 80s by the late astronomer Carl Sagan. In his best-selling book, Pale Blue Dot, Sagan wrote,
"Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light, as if there were some special significance to this small world. But it's just an accident of geometry and optics. Look again at that dot. That's here. That's home. That's us. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark."
One reason for the widespread acceptance of the Copernican principle can be traced to a discovery made on this mountaintop overlooking Los Angeles. Between 1921 and 1926, the astronomer Edwin Hubble used this telescope to make some of the most important discoveries in the history of science. Through the window of the Mount Wilson Observatory, Hubble unveiled the true magnitude of the universe.
At the time that Hubble was doing his work, many astronomers believed that the galaxy, our galaxy, marked the edge of the universe, and there was nothing beyond it.
Edwin Hubble altered this perception of the universe when he used the most powerful telescope of his day to photograph indistinct objects in space. Long thought to be nearby clouds of gas and dust, Hubble determined that these patches of light were actually individual galaxies, many as large or larger than our own Milky Way.
The implication in what he found was that the universe consists of, indeed, billions of galaxies, each with many billions of stars and planets. And it was a universe with a wealth of numbers and variety that transcended the imagination of both layman and astronomer. He, in effect, enlarged the boundaries of the universe.
Edwin Hubble revealed that the Milky Way galaxy, encompassing more than 100 billion stars, including our sun, was a mere pinpoint of light in the universe.
When Hubble found that there were many galaxies, we saw that our galaxy was nothing distinguished at all, just one ordinary galaxy among billions. And that's the ultimate extension of the Copernican principle.
More than 80 years have passed since Edwin Hubble's discovery. Yet today its profound implications still evoke a fundamental question. Does contemporary scientific knowledge actually confirm the Copernican principle's primary claim, that the Earth and the life it sustains exist without purpose or significance in the universe? An outgrowth of the Copernican principle is the belief that habitable planets and complex life are abundant throughout our galaxy and the rest of the cosmos. Perhaps no scientific endeavor has been influenced more deeply by this idea than the research program called SETI.
Well, SETI, which is, of course, the Search for Extraterrestrial Intelligence, is trying to do exactly that. We're searching for extraterrestrial intelligence. In other words, we're looking for aliens that are at least as clever as we are. Now, we try and do that not by trying to go there the way they do in the movies all the time, or waiting for them to come here. We try and find the aliens, if you will, at home on the basis of eavesdropping on signals they might be sending our way. So we use large telescopes pointed at other star systems to try and find these telltale signs that there's some cosmic company out there.
Since 1960, SETI researchers have utilized radio telescopes throughout the world to monitor transmissions from distant regions of the Milky Way. While no definitive signs of intelligent life have ever been detected, these investigations have triggered much speculation about the possibility of extraterrestrial civilizations.
Estimates vary all over the place. Carl Sagan thought there might be millions of civilizations that are kind of contemporaries of ours. I can imagine that within the Milky Way galaxy, the number of contemporary intelligent civilizations, I think, is probably in the thousands, maybe hundreds of thousands. But the bottom line, actually, when people ask, well, why do you think that they're out there, is that the universe is extraordinarily rich, extraordinarily vast. The number of stars that we can see, it's on the order of 10,000 billion star systems. So unless there's something very, very special, miraculous, if you will, about our solar system, about our planet Earth, unless there's something extraordinarily unusual about it, then what happened here must have happened many times in the history of the universe.
The assumption that habitable planets and extraterrestrial life are abundant has inspired not only the SETI program, but also the new science of astrobiology and the search for biological evidence of living organisms, past and present. Since 1995, this search has extended beyond our solar system, as astrobiologists have identified more than 100 planets orbiting nearby stars. Each of them is a gas giant, much like Jupiter. While few scientists believe that these alien worlds can sustain even simple life, their discoveries represent important steps toward answering a question that will shape astronomy in the 21st century. Are habitable planets rare or common in the universe?
I'm an astrobiologist, and the area that I've done the most work in lately is the field of extrasolar planets. What motivates me is just to examine the conditions necessary for life and look elsewhere in the universe and see if those conditions are met anywhere else. And the answer could be yes, and the answer could be no, and either answer is interesting.
Guillermo Gonzalez works as a research scientist in NASA's astrobiology program. His interest in this field is tied to his early fascination with the prospect of life beyond the Earth.
I grew up in the 1960s, and like most other people of my generation, I was really amazed by the Apollo lunar landings, and that really inspired me and had something to do with my getting interested in astronomy. In my early years, I came to believe very strongly that there must be other civilizations out there and that the galaxy was teeming with life. And so I was a strong supporter of the search for extraterrestrial intelligence. My belief wasn't based on any real hardcore scientific arguments. It was just the impression that I had that the galaxy was such a big place. And I didn't give the other side of the equation much thought. In other words, there's two sides of the equation. There's the number of stars, the number of trials, if you will. But the other side is the factors. It takes a lot of factors to have a habitable planet in a planetary system.
For Gonzalez and other astrobiologists, these factors, required for the Earth's habitability, became the focus of extensive research.
We've demonstrated in dozens of different ways the laws of physics and chemistry that pertain in a laboratory anywhere on Earth apply anywhere in the solar system, apply anywhere in the galaxy, and in many cases out to the most distant galaxies that we can see.
There are indeed unchanging physical laws in the universe that apply to the entirety of the universe, that they're not localized to one place.
This consistency in the laws of physics and chemistry has led many researchers to conclude that the factors necessary for complex life on Earth are also the best parameters in the search for habitable planets elsewhere in the universe. Most serious discussions about these factors begin with the same prerequisite: liquid water.
All the searches that are being done for life elsewhere, their starting position is a terrestrial class planet with water.
It is now widely recognized that the chemical properties of water are exquisitely suited for carbon-based life. These properties include water's ability to dissolve and transport the chemical nutrients vital to all living organisms, and its unmatched capacity to absorb heat from the sun, a process critical for regulating the Earth's surface temperature. In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away. You just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life exists in either of these places. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients beyond liquid water might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.
The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents. Deep within the Earth's interior, the movement of liquid iron generates a protective magnetic field essential to complex life. If our planet was smaller, its magnetic field would be weaker, allowing the solar wind to strip away our atmosphere, slowly transforming the Earth into a dead, barren world much like Mars.
We need an oxygen atmosphere, and the oxygen-nitrogen atmosphere that the Earth has is necessary for complex life.
As seen from space, the Earth's atmosphere glows as a thin blue ribbon of light. Measuring less than 1% of the planet's diameter, it is composed of a mixture of nitrogen, oxygen, and carbon dioxide. As a result, our atmosphere ensures a temperate climate, protection from the sun's radiation, and the correct combination of gases necessary for liquid water and complex life.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
If we find life out there, especially complex, or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillionth. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
While a growing body of scientific evidence may support this hypothesis, does the possibility that our planet is rare within the galaxy imply anything about its significance? Recently, astronomer Donald Brownlee considered this question in the best-selling book Rare Earth: Why Complex Life is Uncommon in the Universe.
There's a general feeling that nature wants to make Earth-like planets, and that naturally that life will evolve on them and naturally evolve to something like us. And yet the conditions, the environmental conditions on a planet that would allow more complex creatures similar to people or plants and animals is very rare. And so we wrote the book Rare Earth to point out that the Earth is actually a rather special place.
Brownlee contends that while relatively simple microbial life may thrive on planets throughout the universe, planets capable of sustaining complex life are exceedingly uncommon.
Well, the entire universe is highly hostile to life. If you compare all the known places in the universe, none of them compare to Earth. We live in a very special environment that provides what we need, provides air, provides food, stable conditions, so that the Earth is almost like a giant organism where its systems are interacting in a way that allows animals to survive. The real question is, why did this happen? Was it just a matter of luck or not? If you look at thousands of planets, only a small fraction of them, very small fraction, will be truly Earth-like. So if we are very rare, we did win the cosmic lottery. So we're a lucky planet. We're just in a very fortunate place.
When you consider chance as an explanation for a planet like Earth, you have to look at it in the context of the universe as a whole. While the odds appear astonishingly small that you'd get all the right ingredients to support complex life at this one place in the galaxy, you have to keep in mind that our galaxy is just one of perhaps 100 billion galaxies in the observable universe. Still, logically, I think you have to ask yourself, what if this convergence of factors didn't come about as the result of simply a cosmic lottery or a mere fluke or luck, but what if it's the result of some larger underlying purpose or design? And if the Earth does exist for a purpose, is there any way that we could tell?
On October the 24th, 1995, a rare natural phenomenon unexpectedly triggered a unique search for an answer.
Oh, look at this sky! It started with an experience I had in 1995. I went to observe a total eclipse of the sun in India. It was my first and still only total eclipse of the sun. It was a spectacular event. It's just an experience for all the emotions. Either astronomers who can understand the whole phenomenon, can predict it to within a second of time anywhere on the Earth, or a local native, are equally in awe and reacting in the same way to this incredible phenomenon. It really left a big impression on me.
For 51 unforgettable seconds, Guillermo Gonzalez and thousands of others looked on in wonder at this rare astronomical event. Gonzalez would later reflect upon both the mysterious beauty he had witnessed in the North Indian skies and the factors that had made it possible.
Fabulous! The requirements for producing a total eclipse of the sun are a luminous body, in our case the sun, an eclipsing body, in our case the moon, and then an observer platform, in our case the surface of the Earth, and they all have to be in a straight line in space. The apparent size of the moon in the sky has to be almost exactly the same as the apparent size of the sun in the sky. They're both about half a degree. The sun is 400 times bigger than the moon, but it's 400 times further away. So there's this coincidence people have noted for centuries, but they just said, oh, well, it's a coincidence, and shrug their shoulders.
As Gonzalez examined this rare alignment of sun, moon, and earth, he recognized the importance of these celestial bodies to the existence of complex life on our planet. The gravitational pull exerted by our moon, for example, is strong enough to regulate the Earth's climate by stabilizing its tilt and helping to circulate the warm and cold waters of its oceans, while our planet's distance from the sun permits both liquid water and an oxygen-rich atmosphere.
You have to have the right distance of the observer's home planet from its host star, and you have to have a large moon, and so there's this very strong overlap between the requirements for producing eclipses and the requirements for habitability, for having a planet that can support life.
In 1999, Gonzalez described this relationship between our survival and our ability to observe solar eclipses in the journal Astronomy and Geophysics. His ideas intrigued philosopher Jay Richards.
I've been focusing my research in cosmology, and in particular on applying probability theory to the fine-tuning of the laws of physics. I had a strong sense that this evidence pointed toward some sort of wider purpose to the universe. Then I read Gonzalez's work, and I had the same feeling that he did, that perfect solar eclipses were sort of the tip of the iceberg, the first instance of an entire class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.
In the summer of 1999, Gonzalez and Richards initiated a program of joint research. They began their study by considering a characteristic of solar eclipses little known outside the scientific community. These striking events are not only compelling to observe, they also open a portal onto the physics and chemistry of the entire universe.
Really, you can think of eclipses as a giant natural experiment set up that allows us to observe a part of the sun that's critical towards understanding how its light is produced in its atmosphere.
The fact that the Earth is going around the sun and the moon is around the Earth, and the sizes and the distances between the Earth and the moon and the sun are just so to give you a perfect solar eclipse is a wondrous thing, because it allows us to measure the constituents of the upper layers of the sun's atmosphere.
During a solar eclipse, the moon fits so perfectly over the sun that it shields its blinding light, providing astronomers with a view of the star's atmosphere otherwise impossible to experience. At the moment of totality, the pinkish arc of the chromosphere, the atmosphere's innermost layer, becomes visible, and with it a rainbow-like band called the flash spectrum appears when the sun is viewed through a prism. The eclipse of 1870 led to an understanding of the structure of the sun's chromosphere and the discovery of helium, the second most abundant element in the universe.
The spectrum is probably the single greatest source of information about a star. And it was during a couple of historic eclipses in the 19th century that astronomers figure out how the spectrum of the sun is produced. And they only were able to figure it out because of the particular circumstances during a total eclipse.
These circumstances are both precise and crucial. If our moon was slightly larger, it would partially block our view of the chromosphere and diminish its spectral light. A smaller moon would allow too much light from the sun, destroying our view of the solar atmosphere and the flash spectrum.
And so you have to have a nearly perfect match between the sun and the moon, so you don't hide the chromosphere. And that insight afforded by eclipses in the 19th century is what finally permitted astronomers to figure out how the spectra of distant stars are produced. Really, that opened up stellar astrophysics and allowed us to understand how other stars work, because distant stars, after all, are other suns.
The relationship between eclipses and scientific discovery was also revealed in the spring of 1919. On May the 29th, research teams headed by British astronomer Arthur Eddington photographed the Sun and adjacent stars in the Hyades star cluster during the darkness of totality. Later analysis of the pictures verified that the Sun's gravity bent light from distant stars traveling toward the Earth at the angle Albert Einstein had predicted. Einstein's theory of relativity, an idea that revolutionized our understanding of the universe, had been confirmed during a total solar eclipse.
And that experiment was only possible because the stars become visible during a total eclipse. They're very important in the history of science. And the best place in the entire solar system to view solar eclipses is from the surface of the Earth. I've actually calculated the circumstances for eclipses from all the other planets and all the other moons, about 65 of them, the major moons. And it's an amazing coincidence. The one place that has observers is the one place that has the best eclipses.
Within the gossamer light of a solar eclipse, Gonzalez and Richards recognized a fascinating connection between the factors necessary for complex life and scientific observation. But was this merely an isolated fluke of nature, or a glimpse at a principle and a purpose fundamental to the universe as a whole?
That was the million-dollar question that we continually had before us. What if those things that make a planet habitable also make that planet the best place for making scientific discoveries? That is, what if those rare locations in the universe that are compatible with observers like ourselves are also the best places overall for making observations?
For 3 years, Richards and Gonzalez meticulously tested their idea against evidence gathered from a wide range of scientific disciplines. In the 2004 book, The Privileged Planet, they published their hypothesis. The same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries.
In the book, we detail more than a dozen examples of this correlation between life and discovery. And these aren't quirky, marginal examples. Each treats a condition critical to its respective scientific field. Some deal with remote things, like the nature of galaxies. Others are much closer to home.
While a perfect solar eclipse was the catalyst for Gonzalez and Richards' hypothesis, their observations would never have been possible without another, more familiar example of the correlation between life and discovery: the atmosphere of the Earth.
It's striking when you see pictures of the Earth from the Apollo missions or other spacecraft, and you see this very thin layer of the atmosphere surrounding the Earth that sustains all the life that we know on Earth. And so you need a certain mix of elements to support a complex biosphere like ours. Not just any atmosphere will do.
Our appreciation of the Earth's atmosphere has increased significantly during the last 40 years, as exploratory spacecraft have probed the solar system. These missions have confirmed that within the Sun's family of more than 70 planets and moons, the Earth is one of 7 bodies enveloped by a thick canopy of gas. Yet among these 7, only the Earth's atmosphere can sustain complex life. And only the Earth's atmosphere is transparent.
It's an atmosphere that's made up of mostly oxygen and nitrogen with very little carbon dioxide and very little other carbon compounds or atoms in the atmosphere that gives you a transparent atmosphere. If we had too much carbon in the atmosphere, we get hazes, organic hazes in the atmosphere, like you see on the large moon Titan, for example.
The dense shroud of gas that blankets Saturn's largest moon resembles the atmospheres surrounding Neptune, Uranus, Saturn, Jupiter, and the greenhouse cauldron of Venus. None of these alien worlds know the stars, or even offers a clear view of the sun.
Now, of course, if you were suddenly transported to Titan or Venus or to one of the outlying gas giant planets, the lack of a clear view of the universe wouldn't be much of an issue because you'd be dead. But that's precisely the point. If we're right, if the conditions for habitability and scientific discovery appear in the same places, then you're going to get conditions like you do on Earth, an atmosphere that sustains complex life like ourselves and also enables scientific discovery of the universe around us.
The virtues of such an atmosphere are continually tested. As the Earth moves through space, it is bombarded by radiation from throughout the universe. This radiation is emitted by the Sun and other celestial objects, including supernovas and distant galaxies. It reaches our planet in wavelengths described as gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. Together, they comprise the electromagnetic spectrum. Almost all of these wavelengths are invisible to the eye and either lethal or useless to organic life. Yet within this spectrum of frequencies, a thin sliver of radiation proves essential to plants, animals, and human beings.
In other words, there's really just a very narrow part of the electromagnetic spectrum that's going to be useful for living processes like photosynthesis. It's not as if life could have evolved to use gamma radiation or X-ray radiation or something like that. There's really just a narrow part of the spectrum that would be useful to life processes. Well, as it turns out, that's also the same narrow part of the spectrum that is the most informative about the various structures that we discover in the universe around us.
These specific frequencies that enable plants to manufacture food and astronomers to observe the cosmos represent less than 1/1,000,000,000 of a trillionth of the universe's range of natural electromagnetic emissions. Fortunately, it is the type of light our sun produces in abundance, and that most easily penetrates the filtering shield of our atmosphere to reach the surface of the Earth.
It's a remarkable coincidence that the kind of atmosphere that's needed for complex life like ourselves does not preclude that life from observing the distant universe. It's a surprise. It's something that you wouldn't expect just chance to produce. Why would the universe be such that those places that are most habitable also offer the best opportunity for scientific discovery?
In 1997, Guillermo Gonzalez began a study of the Earth's specific location within the Milky Way galaxy. It would eventually lead him to more evidence of a correlation between life and discovery.
Just as our location in the solar system is optimized for habitability, so is our location in the galaxy. We inhabit a spiral galaxy, which means it's highly flattened. It has a spherical bulge in the center, and it has spiral arms. And we live about halfway between the center of the galaxy and the edge.
Working closely with astrobiologists Peter Ward and Donald Brownlee, Gonzalez compared our position in the Milky Way to other regions within an often hostile galaxy.
The galaxy has a lot of dangers, and perhaps the most dangerous place in the galaxy is the galactic center.
Well, in the center of the galaxy, this density of stars is very high, and there are more supernovas and stuff. And there are things that could harass life right in the dead center regions of our galaxy.
You also have the giant black hole at the very center of the galaxy. And if it were to have a close encounter with a star passing near it, it would rip it to shreds and form an accretion disk around it and emit lots of radiation, particle radiation and electromagnetic radiation, gamma rays, X-rays.
While a black hole, exploding stars and deadly radiation would make complex life virtually impossible near the galactic core, the outer edge of the Milky Way poses other challenges to habitability.
In the outer regions, the situation is much more subtle. We live on a planet made out of iron, magnesium, and silicon, and oxygen. If we went in the more distant regions of our galaxy, out towards the outer edge, the abundances of these elements are lower.
There probably aren't enough heavy elements to build Earth-sized planets that can support life. So there's a happy median between the dangerous galactic center and the outer edge of the galaxy.
Gonzalez, Brownlee, and Ward labeled this region, where complex life is possible within the Milky Way, the galactic habitable zone. Their theory was first published in 2001 and has since received growing acceptance among astrobiologists.
There's a lot more research that needs to be done to determine just how wide the habitable zone is. But I think there's general agreement that yes, there are definitely places in the galaxy that you cannot have civilizations because they're very dangerous. And there are places where you just have a very low abundance of heavy elements.
While these obstacles to habitability are minimized far from the core and edge of the Milky Way, Gonzalez has also identified large areas within the galactic habitable zone itself, which are less hospitable to complex life.
Even within the habitable zone in the galaxy, it's broken by the spiral arms, which are dangerous places. That's where most of the supernovae go off in the galaxy. That's where the star formation is taking place.
We don't want to be too close to a spiral arm. We want to be outside the spiral arm at about the right region of the galaxy.
It appears this is precisely where the Earth is located, in the relatively safe and uncrowded region between the Sagittarius and Perseus arms of the Milky Way.
Location is everything, and so we occupy that special place in the galaxy where habitability is optimized, threats are minimized, and we have enough building blocks to build an Earth.
Guillermo Gonzalez and Jay Richards have conducted research on another facet of the galactic habitable zone. They now argue that the Earth is also located in the best setting within our galaxy for astronomical research.
As it turns out, our position in the universe is not only critical for life, but it's also surprisingly important for making scientific discoveries. We're located near the midplane of the galaxy, a very highly flattened galaxy, between spiral arms in a region with very low dust extinction. While we are in the plane of the galaxy, that does not obscure a large part of the sky, so we can have very clear views.
For more than a century, this nearly ideal platform of observation has enabled astronomers to study the structure of the Milky Way. Looking toward the constellation Sagittarius on a clear night, for example, we see that the stars in our galaxy are not uniformly distributed across the sky. Instead, they appear as part of a concentrated band, a flattened disk of stars, dust and gas, 100,000 light-years in diameter.
The Milky Way band in the night sky is us looking edge-on into the plane of the galaxy. If we were living in the center of the galaxy, things would look much more spherically distributed. And so it would be very hard to distinguish things that are inside the galaxy from things that are outside. And it's also very dusty, much dustier towards the galactic center than it is in our region. And so the views of the distant universe will be much more difficult to obtain, to be much more compromised.
Similar problems would exist for astronomers working on a planet located within any of the galaxy's spiral arms. Here, denser concentrations of dust clouds and gas illuminated by stars would make it difficult to determine the shape of the Milky Way, or to distinguish the stars in our galaxy from the rest of the universe.
On the surface of the Earth, we're really in the optimum position for seeing both the nearby structure of the Milky Way galaxy, as well as seeing the distant cosmos as a whole. So once again, we see that the best location for habitability and for producing a habitable planet is also the best overall position for scientific discovery, in this case, at the galactic scale. For centuries, the fact that we can discover things about the universe has really been something of a mystery. Why would beings like ourselves be able to discover a universe like this? Why is what we think about the universe, why would it correspond to the way things really are?
Our ability to discern and understand the universe is a fundamental part of what makes the universe tick, so that we're linked into it. This isn't just a sort of an accident, a trivial little byproduct. It is something that is linked to the great cosmic scheme of things. Now, I've no idea how that linkage works, why it's there, or anything of that sort, but I'm very, very struck by the fact that we can understand the universe in such exquisite detail and at such a deep level.
The spectacular progress of modern astronomy and physics is the product of a universe accessible to the human eye and mind. It is a universe governed by laws and forces that literally hold our planet Earth and the entire cosmos together, and are finely calibrated to allow for both complex life and scientific discovery.
If you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't have the strong nuclear force, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You would have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you're to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed, even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
Now, this is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces are all important, the masses of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work. And not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible part I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
Many who have pondered this mystery of an intelligible universe argue that it cannot be easily explained away.
From naturalistic assumptions, you would not expect the universe to be understandable by human reason. After all, within the standard naturalistic story, human reason was developed to be able to hunt prey, get around in the everyday world, attract mates.
We have certain skills, for example, we can jump streams and catch falling apples and so on, which are necessary to getting by in the world. But why is it that we also have the ability to discern, for example, what's going on inside atoms or inside black holes? These are completely outside the domain of everyday experience, totally surplus to requirements, not at all necessary for good Darwinian survival.
Discoverability of the universe is something we didn't need for our existence. It's something additional to it. It seems then that whatever the source of the universe is, it intended that it contain observers who can discover.
You put observers in the best places for observing. That is, if you're going to do things intelligently, that's what you do. The nature of our planet, the nature of its atmosphere, the location in the solar system, the type of solar system it's in, even the type of star that we're around and the location within the galaxy are optimal for making a wide range of scientific discoveries. It turns out that those are also all the most important conditions for a habitable planet, that is, for a planet that's conducive to beings like us and without which we could not survive. I think that's just the sort of pattern that ought to suggest to people conspiracy rather than mere coincidence.
There's something about the universe that can't be simply explained just by the impersonal forces of nature and atoms colliding with atoms. And so you have to reach for something beyond the universe to try to account for it.
Such an approach lies at the foundation of modern science. In his search for a more elegant description of the solar system, Nicholas Copernicus was motivated by his desire to comprehend what he called the mechanism of the universe, wrought for us by a supremely good and orderly creator. The system, the best and most orderly artist of all, framed for our sake.
And so he imagined this analogy of a workman, a craftsman, making something that worked well and was beautiful. And that analogy, it wasn't one of his conclusions, that analogy was one of his assumptions.
The founders of modern science, like Copernicus and Kepler and Galileo and Newton himself, believed that the universe was the product of a mind, that it was intelligible to beings like ourselves because the universe itself was the product of an intelligent being.
They were driven by this notion that this was essentially a theological quest. They were uncovering God's handiwork in the way the world worked. I mean, what a thought, that we can glimpse the mind of God. We can actually figure out how God put the universe together. There's a hidden subtext in nature which can be exposed through this procedure we call science.
Though most scientists no longer think in such explicitly theological terms, recent evidence may again point to an Earth far different from the contemporary image of a pale blue dot lost in a cosmic sea.
We've often been told, especially in the 20th century, that the universe does not have us in mind. That is, that we exist in a very large universe and that the universe was not designed for beings like us. We are simply life that happened to come about on a tiny little planet surrounding a tiny insignificant star in a run-of-the-mill galaxy within a very large universe that was not intended. Our argument suggests something completely different. It suggests that the universe was intended, that the universe exists for a purpose, and that purpose isn't simply for beings like ourselves to exist, but for us to extend ourselves beyond our small and parochial home, to view the universe at large, to discover the universe, and in fact, perhaps, to consider whether that universe points beyond itself.
As we gaze ever deeper into the universe, we are inevitably drawn back to timeless questions. What is the source of the cosmos? And what is our purpose within it? While answers will always be debated, valuable new insights are now at hand, emerging from a corner of the universe where complex life and scientific discovery have converged on an extraordinary planet called Earth.
The specific challenge we have in the Origins program is to actually look for planets like the Earth around nearby stars. The nearest 50 to 150, maybe a few hundred stars. We want to be able to look at those stars with a mission we call the Terrestrial Planet Finder, block out the light of the parent star, and see if we can see the light of individual planets orbiting those stars. From that information, see in fact if those planets could be habitable or in fact are inhabited by at least some primitive life forms that could have affected the atmospheres of those planets. You certainly want to understand how many rocky-sized planets the size of the Earth, give or take a factor of 2, there might be. So that's number one. Of those, how many have atmospheres at all? And our expectation is above a certain size, most rocky bodies will be able to retain an atmosphere because we know there's a lot of volatile material, water and all the things that accompany that are available. So we ought to expect to see atmospheres, but that's the next thing we want to look at. Then finally, what is the composition of such an atmosphere? Does it show water vapor? Does it show carbon dioxide? Do we see either oxygen or ozone, which are really signposts of non-equilibrium chemistry that's probably driven by some kind of photosynthesis? If we find an Earth-sized planet in roughly what we call the habitable zone, you can call it the Goldilocks zone. It's not too hot, it's not too close to its parent star, it's not too cold, it's not too far away from its parent star, and that region is roughly bounded by the orbit of Venus or the orbit of Mars in our own solar system. If we found a habitable, a terrestrial planet, our planet our size, in roughly that region, there'd be a good prospect that, depending on how other variables played out, that would be a habitable planet. Is life an imperative from the laws of physics and chemistry, or is it a very rare fluke thing? Again, we don't know. Theoreticians will say, yeah, life should be everywhere. If you give water, elements, and energy, life should just happen. Might be that way. Might be there's some little magic ingredient we don't know about. But we'll try and make that susceptible to an observational program over the next 10 to 20 years. 10 years from now, we'll know what stellar systems nearby have planets at the level of a few Earth masses from the SIM mission. We'll know the average number of Earth-like planets around stars like our Sun in general from the Kepler mission, and we may be getting the very first observations from Terrestrial Planet Finder itself, asking the question, where are the actual Earth-like systems? Do they have atmospheres? What's in those atmospheres? And does the content of any of those atmospheres suggest the presence of life? Oh, I think this is the most exciting scientific question that we can address in the 21st century in terms of astronomy, at least. Cosmology was really the study of where did we come from. We've been studying that really for almost 100 years now, modern cosmology. And we're now simply starting a new investigation of understanding the formation of planets and the search for life, and I think it's a 100-year quest, and we're just at the outset of it, and that makes it a very exciting time to be involved. I think what is very much driving people's interest is this whole question is, are we the only place in which a creation of life and intelligence and self-awareness has ever taken place? And we will find out if it's happened only once or another time only 3 light years away, or whether the closest other life is on the other side of the galaxy or wherever. I think there's a British biologist, I believe it was Haldane, who said, either we're alone or we're not. Either way, the implications are staggering.
The worldview of the scientists, even the most atheistic scientists, is that essentially of monotheism. It is a belief which is accepted as an article of faith that the universe is ordered in an intelligible way. Now, you couldn't be a scientist if you didn't believe these two things. If you didn't think there was an underlying order in nature, you wouldn't bother to do it because there's nothing to be found. And if you didn't believe it was intelligible, you give up because there's no point if human beings can't come to understand it. But scientists do, as a matter of faith, accept that the universe is ordered and at least partially intelligible to human beings. And that's what underpins the entire scientific enterprise. And that is a theological position. It's absolutely clear when you look at history. It comes from that theological worldview. That doesn't mean you've got to buy into the religion or buy into the theology, but it is very, very significant in historical terms that that is where it's come from, and that scientists unshakably today retain that worldview as an act of faith. You cannot prove it logically has to be the case that the universe is rational and intelligible. It could easily have been otherwise. It could have been arbitrary, it could have been absurd, it could have been utterly beyond human comprehension. It's not. And scientists just take this for granted for most part, but I think it's a really important point that needs to be made.
The great Copernican cliché, and you'll find this in many high school science texts, you'll find it in Stephen Hawking, you'll find it everywhere, is that Copernicus dethroned humankind. He dethroned Earth from its special place at the center of the universe. It was a demotion. And Carl Sagan talks about a great series of demotions for humankind, beginning with Copernicus. But if you think about it, to be demoted means to be taken down a notch. The pre-Copernican Earth couldn't be taken down a notch. It was already at the very center, at the low point of the universe. It was a kind of cosmic sump. The philosopher Pico said, "We live in the filthy and excrementary parts of the lower world." And so to move the Earth from that place to the status of a planet was a promotion, not a demotion. So in fact, the historical record, the textual record of Copernicus and those who were his immediate followers, like Galileo and Kepler, runs counter to the cliché that you read in almost every textbook, that Earth was somehow demoted or dethroned by Copernicus. Well, let me be very plain. I don't like the term Copernican principle because Copernicus isn't responsible for it. It's an actual misinterpretation of what Copernicus taught. Copernicus, in spite of what some historians of science tell you, really believed that the creation, in some profound and meaningful sense, was for us. Propter nos is the term he uses in Latin. Now, he also believed that God was wise enough and powerful enough that he could serve 3 or 4 or more purposes with any given creation. So to say that the creation was for us never meant for Copernicus that it was merely for us. But we human beings, as far as Copernicus was concerned, were included in that overall plan.
The Kalam argument is deceptively simple in its formulation. It consists of basically 3 steps. Premise 1 is that whatever begins to exist has a cause. Something cannot come into being uncaused out of absolutely nothing. Whatever begins to exist has a cause. Premise 2 is that the universe began to exist. And from those 2 premises, it follows logically, therefore, the universe has a cause of its existence. Whatever begins to exist has a cause. The universe began to exist, therefore the universe has a cause of its existence. And the remarkable development that has occurred during the 20th century is that for the first time, we now have solid scientific evidence for the truth of that second premise, that the universe began to exist, so that this is no longer a matter of armchair cosmology pursued by philosophers. It's now a matter of simple scientific fact pursued by cosmologists.
If you reverse the motions, the outward motions of the galaxies, and go backward in time, they come closer and closer together. And you reach a point finally where they're nearly infinite in density and temperature. And farther than that you can't go. So there is a beginning. There is a point in time from which it all started. And that's a remarkable thing because it has a very strong theological flavor to it. And that intrigued me because I am a an agnostic. And if there was a beginning, a moment of creation in the universe, then there was a creator. And a creator is not compatible with agnosticism. And I found that message so interesting that I felt a strong compulsion to share it with others. And so that's why I wrote that book. Just as I can't believe that there was a creator, I can't believe that this all happened by chance, which implies there was a creator. So you see, I'm in a completely hopeless bind, and I've stayed there. Again, I find it hard to believe that this is all a matter of atoms and molecules. And so I try to fit into my concept of the world the conclusion that there is a larger force of some kind, which we can call God, or you can call it whatever. But I can't accept that. I'm what's called a materialist in philosophy. I believe that doesn't mean I like Cadillacs and big cars. My students always used to think that. It means that I believe the world consists entirely of material substances. And when you specify those substances, the atoms and molecules, and the laws by which they interact, you've done it all. There isn't anything more to be said or inserted into your model of the universe. And that's what my science tells me, and I've been a scientist all my life. But I find it unsatisfactory. In fact, it makes me uneasy. I feel I'm missing something, but it will not. I will not find out what I'm missing within my lifetime.
The fine-tuning concerns two features of the observable universe. First, as you give the laws of nature mathematical expression, there appear in these equations certain constants, like the gravitational constant. And these constants are independent of the laws of nature. That is to say, the laws of nature, the equations, can be true, even though these constants take a wide range of values, so that the values that these constants have are independent of the laws of nature themselves. The laws of nature do not determine what the values of these constants are. Secondly, in addition to these constants, there are certain arbitrary quantities which seem to just be put in at the creation as initial conditions on which the laws of nature then operate. For example, the amount of entropy in the universe, or the balance of matter over antimatter in the early universe. And what scientists have discovered within the last 3 or 4 decades is that in order for intelligent life to exist, all of these cosmological quantities and constants have to fall in to an extraordinarily narrow, I cannot convey how almost infinitesimally narrow a range of values. Otherwise, the universe would be life prohibiting. And if you deny the hypothesis of cosmic design, you're basically left with two alternatives. Either that this fine-tuning is the result of physical necessity, that is to say, there's some unknown theory that will explain why these constants and quantities had to have the values they do, or else you've got to say that this just occurred by chance alone. It is the result of sheer accident. Well, that first theory doesn't seem too plausible because there just isn't any theory that would explain why all of these constants and quantities have the values they do. They appear to be just arbitrarily put in at the creation as initial conditions. With respect to the second alternative, chance, again, most theorists recognize that the odds against the universe being life-permitting are just so fantastic that chance simply cannot be faced unless you say that our universe does not represent the only roll of the dice. And so what many theorists have been driven to is multiplying our probabilistic resources by saying maybe our universe isn't the only roll of the dice. Maybe there are out there parallel, unseen, undetectable universes, and that our universe is just one in this cosmic crapshoot in which there is an infinite number of other worlds in which the cosmic constants and quantities vary randomly, and so by chance alone, somewhere in this infinite ensemble of universes, our universe would appear by chance alone, and here we are, the lucky beneficiaries and recipients of this chance hypothesis. So that in order to rescue the chance hypothesis, physicists have been driven beyond physics to metaphysics, to this extraordinary hypothesis of a world's ensemble of an infinite number of randomly ordered worlds in order to explain away this appearance of design.
The multiple universes idea scientifically is very problematic because we could never test it. Other universes could never be observed, so they'd always be on a theoretical basis. So it'll be untestable, and it's a kind of metaphysical argument. So it's actually a metaphysical response to something that we see in our universe, namely the fine-tuning of the constants of nature.
I think if you talk to the people who do this at a day in, day out business, the biochemists who understand what are the things you need in chemical processes to make life possible, they would all say that biochemistry favors carbon-based. Carbon-based life is really extremely likely to be the chemistry of life elsewhere, simply because the carbon atom has a specific bond structure, the carbon bond, which lends itself to very complicated, intricate structures, rings, long chains, all the things that make up organic chemistry on Earth is not replicated using any other element as a substitute. People talk about silicon life. Very unlikely to happen, unless maybe carbon life built computers and then the computers took over. But in terms of just springing up, the chemistry of carbon is simply unique. And that applies on Alpha Centauri or the most distant quasar. The carbon bond is the carbon bond, and there's no substitute for it in the 92 elements. We know the elements.
Sometimes people will object that we have what's called a sample size of one. In other words, usually when you're developing an argument, you want to be able to compare the thing you know with some other things that you know about. In our case, of course, so far as we know, there's one habitable planet in the universe, at least only one that we know about. So the question would be, how with a single example like this can you make such a wide-ranging claim about the universe as a whole? It's important to understand, first of all, that there are many things we know about what any kind of life is going to need, because the laws of physics and chemistry are universal as far as we can see. It's not like there are different elements in different parts of the universe. No one's looking for other elements to fill in places in the periodic table or something like that. Moreover, any type of chemically based life form is going to need to build information-rich molecules. So there just going to be some basic constraints on any type of life. So in fact, if we're careful, we can actually generalize about any kind of conceivable life in this particular universe, so that it's not simply that we're sort of trapped in this one little corner of the universe, but in fact, we can make these generalizations at least at the biochemical level. Secondly, while we do in a sense have a sample size of one, we can do a whole lot of comparing about different places in the universe. We have a pretty good idea, for instance, of what solar eclipses are going to look like someplace else on another planet. We have a pretty good idea of what sorts of things you could see and measure in the center of the galaxy or in other types of galaxies, the sorts of things you could learn and have difficulty learning around different types of stars. Our argument isn't simply that all these types of scientific discovery would be impossible everywhere else. It's comparative. We're saying when you consider all the types of things you need to discover, the sorts of questions that you want answered in science, that our environment provides the best overall conditions for scientific discovery in a wide range of scientific disciplines. So we think we can make some fairly certain generalizations about the things that obtain here and the things that would need to obtain anywhere, both for life and for scientific discovery. We claim that our position in the universe is optimal for making scientific discovery. But when we say optimal, we mean that in a particular sense. And it's the idea that engineers often talk about as constrained optimization. And what constrained optimization refers to is the fact that when someone designs something, when an engineer, for instance, designs a laptop computer, he's not simply going to design it for one parameter, for one variable. The best laptop computer is not going to simply be the fastest laptop or the laptop with the largest screen, because there's going to be multiple competing objectives. So the best laptop is going to be the best overall compromise of these competing objectives. So the best computer would be the one that balances cost, ease of use, screen size, resolution, CPU speed, price, and these sorts of things. When you find the best sweet spot where all these things converge, that's going to be the best laptop. In the same way, we say that the Earth is the best overall environment for making a wide range of scientific discoveries, from geology at the small scale to nearby planetary science, to discovering the laws of gravity from our planetary neighbors, to doing galactic astronomy and nearby stellar astronomy. So when you add up all these different domains of the natural world that you need to discover things about and to be able to probe, and you consider all these things, habitable environments are a sweet spot where all these different competing conditions for scientific discovery are met, and that makes habitable environments the best overall places for scientific discovery in the universe. Our argument is based upon very specific empirical pieces of evidence. In other words, I think this evidence has very important implications, but it doesn't have very specific philosophical or metaphysical presuppositions. The argument is based upon very specific empirical facts and observations about the location of the Earth within the solar system, of the stars around us. That is, it's based on pieces of evidence like the location of our sun within the galaxy, the type of galaxy that you'd need to have a habitable planet, the location within that galaxy that you'd need to have a habitable planet, and the sorts of things, on the other hand, that you'd need to make scientific discoveries. These are things about the physical universe. These are not pieces of evidence based upon religious text or based on highly controversial philosophical assumptions. So the argument is based upon specific empirical evidence about the physical world, but it has very wide-ranging philosophical and metaphysical implications. But there's a difference between an implication and a presupposition.
It will be a good test of our proposal if in the coming years, the coming decades, the case becomes stronger or weaker. As we learn more about the requirements for habitability in the universe, about what kind of conditions you need to make various scientific measurements, if our argument is correct, that there really is this correlation between habitability and measurability, then our case will become stronger as our resolution, our knowledge in science increases. If we're wrong about it, then our case will become weaker as knowledge increases. So the coming few years will be a good test, because there is a lot of research taking place in astrobiology. So there's no question new data will be coming in, and there will be the opportunity to see if our hypothesis passes the new tests or not. I'm confident that it will.
It was scheduled for February 14th, so it was our Valentine's Day observation. By that point in time, Voyager was so far away that when it turned back to look at home, home was just a tiny little dot in the sky. And the data came back. We had to play it back several times over several deep space stations. And at the time, it was my job as working for the Voyager imaging team to go through the images that the spacecraft acquired during cruise, it was a routine part of my job to go through the images and make sure that they had been taken successfully. So it fell to me then, when the data came back, to be the first person to look at the pictures and to look for these tiny pinpoints of light that we knew should be where the planets are. And so when I got to the 3 that I knew should have the Earth, initially, the first picture I thought, well, where is it? But there was kind of this spot in this ray of scattered light in the optics. And I thought, well, maybe that's it. And then sure enough, it showed up in the other 2 filters. And so then it was certain that it was the Earth. And it was just so wonderful to see, even though I knew it was just scattered light in the optics, to see our Earth sort of bathed in this ray of sunshine just gave me chills down my spine. It really made it seem special.
Between 1921 and 1929, Mount Wilson Observatory was the site of some of the most important discoveries in the history of astronomy. Here, more than a mile above Los Angeles, Edwin Hubble used this telescope to revolutionize scientific understanding of the structure, size, and origin of the universe. Working tirelessly from his wicker chair, Hubble determined that our Milky Way galaxy, thought by many astronomers to constitute the entire universe, was actually just one of countless billions of galaxies in a vast cosmic sea. Hubble also demonstrated that these galaxies were receding from each other, a fact that strongly implied the universe had a definite beginning. For a better perspective of the cosmos Edwin Hubble unveiled, let us embark on an imaginary journey from the top of Mount Wilson to the farthest reaches of the known universe. Traveling at the speed of light, 186,000 miles per second, how long would this journey take? Albert Einstein demonstrated that time would be dramatically altered for anyone traveling at such a speed. But for the sake of simplicity, we'll set aside this effect by measuring time with earthbound clocks. We depart Mount Wilson on January 1st. Hurtling through space, we quickly pass the orbit of Mars in just 4 minutes, 30 seconds. We continue on, past Jupiter and the other gas giant planets, Saturn, Uranus, and Neptune. And 5 hours and 30 minutes after leaving the Earth, we fly past Pluto and its companion moon. Our journey has taken us more than 3.5 billion miles to the outer limits of our solar system. And back at Mount Wilson, it's still January 1st. We now take our first steps into interstellar space. Behind us, our neighboring planets and the Sun quickly disappear from view. The void of space is broken only by the glimmer of stars so distant they do not yet appear to move, even though we continue to travel at the speed of light. A year passes, then 2 years, 3, 4 years. Finally, on April 19th of the 5th year, we reach the Alpha Centauri system, the nearest stars to our Sun. We have traveled nearly 25 trillion miles, yet our journey has barely begun. We are now 10 light years from the Sun, far enough out in space that the stars within our galaxy appear to converge. 100 light years from the Sun, patterns of gas and dust from an arm of the Milky Way galaxy surround us. 1,000 light years. The galaxy's arms and central disk become more defined. Yet it is not until we've traveled at the speed of light for 100,000 years that the entire spiral shape of the Milky Way is recognizable. From here on, each point of light we see is no longer an individual star, but an entire galaxy composed of billions of stars. 5 million years after beginning our journey, the Milky Way is recognized as part of a cluster of at least 30 galaxies, known as the Local Group. Bound together by gravity, the galaxies that comprise the Local Group span a region of space more than 3 million light-years across. 50 million light-years out, we encounter the large Virgo cluster, containing more than 2,000 galaxies. And so it goes, as we continue to travel deeper into the cosmos. We pass cluster after galactic cluster, each a building block of a far greater framework. 1 billion years pass. 5 billion. 10 billion. Finally, after 14 billion years, we are able to discern the large-scale structure of the entire universe. At least 100 billion galaxies stretch in thread-like chains across the cosmos, forming a tapestry of unimaginable dimensions. Today, scientists still ponder the source of a universe where uniformity and precisely balanced laws and constants enable us to survey its size and structure, to contemplate its origin, and to appreciate the profound reality of our existence within it, upon a remarkable blue planet, well suited for both life and discovery.